Now, for the first time, we are concerned with a real, you could say, a full field in the sense of the word, because the phrasing has been introduced mainly for the three-dimensional case. And here I'm talking of three spatial dimensions as they are, not just to visualize something special. Now you will see the problem is, if you imagine a scalar field in 3 dimensions, it will not be so easy as before to visualize this function, because the trick with the curved surface won't work anymore. What you would need sort of a curved space, which is, okay, I'm not talking about Einstein relativity now, we could, but it's more easy if you take the technical approach. It's quite easy. You have the possibility just to display a spatial coordinate system, and then imagine you just choose any point in space with 3 coordinates, x, y, z, and then you calculate this term. For example, this one, it's just a number, and you assign this number by 2 possible ways. Either you define a color map, so you say low numbers are blue color, bluish tones, higher numbers are reddish, in just imagining everything's positive, for example. So you get a so-called color map of such a spatial scalar field. The other way imagining it is just using a very fine pencil and putting this functional result as a number, just putting it there in space. So you have these hovering numbers everywhere in space, and this is also a good picture. So what is it about in the application for our purposes? Mainly to describe an electrostatical potential of a certain charge distribution, for example, and then asking the question, in which spatial direction and how strongly does this electrical potential, which is nothing else than potential energy in joule per coulomb, you know, like normalized to the unit charge, with which strength in this direction in space does it increase? Yeah, what is at a given position, what is the maximum direction and value of increase of this potential? Actually, in the technical application, it's more about direction and strength of maximum decrease. That's why we always have a minus sign before the gradient in the technical application. Some people don't know this, especially mathematicians often don't know it, and then they just ask the wrong questions about technical applications. I've often found physical exercises in mathematics books which contained many sign errors, sign mistakes, but different topic. Okay, so we want to determine the gradient, the spatial gradient of this potential function, spatial function, scalar field in 3D. And now this is something which is sometimes called the so-called direction derivative. In case you heard it, I call it something else. I call it the rate of change per unit length. I gave this in cursive letters for you to note. This is sort of a slope. The problem is that our usual coining of the term slope doesn't work anymore. You know why? It's because how do you display graphically a slope when your function is sort of the 4th dimension in a 3-dimensional vector space? It's not possible to purely graphically display it, but you can agree with me that what I'm talking about is the perfect analogy to a classical slope, because a slope has always been a rate of change of a certain function referring, or yes, in relation to a change, a sort of a unit change of a certain independent variable. So now this time it's sort of a combination of all independent variables, x, y, z, changing, but for a total of a unit length in that direction. That's the idea behind the so-called direction derivative. Well, all we need is the gradient to this end. So the function is here. I gave you a point in space also, and a v vector, spatial direction vector, which has a certain absolute value not equal to 0, so it's not a unit vector. And as a side note, it will be necessary to use a unit vector instead, because we are looking for the rate of change per unit length. That's the reason why. You must think about it for a while, probably, to understand that it's necessary to normalize this V vector in order to get the correct result. You can check it also by hand. Okay, so that's the term. It's quite easy actually because it's separated concerning X and Z. Anyway, it's a good idea now, at least once, to train the technique of taking partial derivatives also with 3 independent variables. So the partial X derivative will be, what is it? Well, I must use the product rule in this case because this is a term dependent on X and this also. So I differentiate the first one, e power X partial derivative for X then is still e power X. You know why? That's the general differentiation rule for exponential function. It stays as it is, but I have differentiated it times other factor as it is, leave it alone, x squared plus y squared. Then plus, next part, leaving this alone, factor of e power x times this one differentiated but partially for x. So this one gets me 2 times x, and this is additively constant. Remember, we must treat y and z as constants. So that's it. And even this goes away, it disappears when differentiating for x because it's additively constant regarding x. So that's all. And now I can always pull identical exponential terms outside. So I have e power x times, and in parentheses I get x squared plus 2x plus y squared. I just sorted this for, well, descending order of powers and also alphabetically as usual. So now next, simpler, because when taking the partial derivative for y, I do not need the product rule. Please understand why. Because this time, this is no more a function. This is just a constant factor. X is treated as a constant. So it just stays there, e power x. And then I take the derivative of this one, of course, for y this time. Additive constant vanishes, y squared gets differentiated to be 2 times y. And still, this is an additive constant, disappears. Done. And thirdly, even more funny, perhaps, but interesting to learn about it, the partial derivative with respect to z must be simply negative 2z. Why is it? Well, this whole term is independent from z, which means it counts as an additive constant with respect to variable z, and so it disappears simply, while negative z squared gets differentiated to be negative 2z, differentiate over z. Okay, so that's it. And then the gradient gets to be this really spatial vector here. And now it's perhaps it's the right moment to coin the terminus gradient field, because once again, right? Because you must understand that the gradient itself is a fully valid vectorial spatial function. It means you can calculate it in any point in space, and it may be different in any point in space. It is actually so different in direction and in strength. And this is what I told you. The gradient describes you for a whole application example for a whole electrical charge distribution. The strength and direction of the electrical field, actually, the famous capital E, electrical field strength. That's it. That's actually the negative gradient of the electrical potential, which is, by the way, also the famous potential in the physical unit of volts. You know, volt, which is actually the same as Joule over Coulomb. So that's quite an easy connection between these physical properties. Now, this is a mathematical exercise, so let's proceed. I use this notation, which is common for the so-called direction derivative in direction of vector v, but I told you it is necessary for reasons of well, scaling to divide everything by the absolute value of this vector v. So actually, it's like we want this v vector to determine a spatial direction, but we don't want its absolute value to play any role. That's it. And that's the way we get the rate of change per unit length. Now, what we have to do is, after having calculated the gradient, remember, the gradient gives you the direction and strength of maximum functional increase. Actually, we can now insert our point in space with coordinates 1 to 0. I'm doing so. Well, I get e power 1 times, then I have 1 squared plus 2 squared, which is 1 plus 2 is 3 plus 4 is 7. So I get 7 times Euler's number e. This is just because it's mathematical, so I have Euler's number inside. Don't be confused what it means. It means nothing. It's just this way of representing it. And then e power 1 times 2 times 2. So I get 4e for the second and 0 for the third component because z equals 0. So that's easy. I get e times vector 7, 4, 0. Here you see this is the direction in space, and also the absolute value of this is the strength. Here it's given of maximum change, better speaking, maximum increase of this function. So, and now you should know that the simple scalar product of two vectors helps us to solve this problem, because we just have to take, here it is, e times 7, 4, 0, we use the gradient, take the gradient times the given v vector in the sense of a scalar product, which you know that it, the point is that the scalar product takes into account the angle, in this case, a spatial angle, you could say, between this gradient and the desired direction. And the larger this angle is, the lower the cosine of this angle will be. And this is what's included in the geometrical version of the scalar product. So it means, in other words, if by chance I would choose the v vector to be identical in direction with the gradient, then I would expect a maximum result. And that's what I would get, because the scalar product of the gradient by more or less itself, divided by its own absolute value, would be a maximum result. So in this case, I even get a negative result. You see, because you know what this is? Normalization by the length of this v vector, but then also 7 times 0 plus 4 times negative 3 plus 0 times 4. You see, this is just negative 12, and then over 5 and times e. So this is a negative result. It means that the increase of our function per unit length in this spatial direction is actually negative. It means it's a decrease. And the reason is that, how do you say, there is a obtuse, is that the correct term? Yes, I think it follows that phi, which should be the angle between gradient of f and vector v, like this. This will be quite surely an obtuse angle. I hope this is the correct word. Obtuse should be an angle between right angle and straight angle. So why is it? Well, simply because it must be the case that the direction of v is, let's say, very different from the direction of the gradient. You know, so it's more the case that v is directed opposite to the gradient than it is directed in gradient direction. Because if it were, roughly speaking, directed in gradient direction, we would surely have a positive result for the increase. Yeah, you can imagine easily. So if this would be the gradient of f, and then my v vector would be like, for example, sort of like this, it's quite obvious that it has a negative component in direction of the gradient. And in this case, the angle of phi is clearly between pi half the spatial angle, yeah, so you take it the way it's as small as possible. That's the way you take it. But anyway, it's between right angle and straight angle. You understand what I mean? I'm hopeful. Okay.